Hello. This video is going to be called Ozonolysis of Alkenes. This is the last of the reactions of alkenes, and it's different from the other ones. All the rest of the reactions of alkenes that we've seen so far are addition reactions, where you have the double bond and you add one group to one carbon and one group to the other carbon. They may be the same group as each other, or they may be different. If they're different, you have to have a rule for which carbon gets which thing, and they may be syn addition, or they may be anti-addition. But ozonolysis is none of those. Ozonolysis is a reaction where you take the alkene, carbon-carbon double bond, and you literally split it in half, add oxygens in on each side. So you make two new products, one from each side of the alkene, except in some cases it's only one product because it might be in a ring. But we'll get to that in just a minute. Before you start, let's go ahead and read section 6.5b, pages 233 to 235. Just a couple pages there. So here's the main idea of ozonolysis. As I said, it starts with an alkene, and this is just a generic alkene. These four positions can be carbon groups or hydrogens in any combination. And you react it with the element oxygen, but in a allotropic form called ozone. I'm sure you've all heard of the ozone layer. This is the material that makes the ozone layer the ozone layer. It's an allotrope of O2, different form of oxygen. And then in a second step, you add a compound called dimethyl sulfide. So it's two methyl groups on a sulfur. And so this is a two-reaction, one-pot synthesis, in which first you add one reagent, you let it react. We will see what happens after that first step here in a minute. And then, once that's done, right in the same pot, you add in some of the second reagent, in this case, dimethyl sulfide. And when the whole thing is done, that you have split the molecule into two molecules, so you're breaking it apart into two smaller pieces. And on one side, you add, where there was a carbon-carbon double bond, now there's a carbon-oxygen double bond. And on the other side, where there was a carbon-carbon double bond, there's another carbon-oxygen double bond. So essentially you're adding in two double bond O's where there was one carbon-carbon double bond. Now these products, depending upon what other groups are on these positions, may be aldehydes or ketones or one of each. So if both of these are carbon groups, then it's a ketone. If one is a carbon group and one is a hydrogen, then it's an aldehyde. If they're both hydrogens, then it's a special aldehyde called formaldehyde. Same thing could be true on the other side, and really it depends on what was on the original alkene in terms of what you get for your products. Let's look at the first reagent of ozonolysis. It's called ozone. As I said, it's an allotrope of the element oxygen. Allotrope just means a different form of an element. So think diamond and graphite, different forms of the element carbon. This is different forms of the element oxygen. O3 is a gas, just like O2 is a gas. And it's formed by running electricity through a sample of oxygen. So I found a picture of an ozonizer on the internet, and basically it's just a box that you let oxygen in one of these two ports. It runs through an electric current and comes back out again as ozone. So you would attach the ozone side to whatever flask you want to put the sample into, and you let the ozone go into that flask, and it would react with your alkene. Here's the Bounce equation. 3 molecules of O2 becomes 2 molecules of O3. Here's the Lewis dot structure in case you've forgotten. Ozone has 3 oxygens, not in a ring, one in the middle, one on the side with a double bond to it, and one on the other side with a single bond to it. This is a regular oxygen with 2 bonds and 2 lone pairs. This is a negative oxygen with 1 bond and 3 lone pairs. This is a positive oxygen with 3 bonds and 1 lone pair. And so the charges balance out and it's a neutral molecule. This is drawn in a straight line. We know that it's actually trigonal planar, which means angles of about 120 degrees. And so this is a more realistic picture of the angle in the molecule. Also, it's true, although not drawn here, that this has another resonance structure in which that's a double bond and that's a single bond. That's neutral and that's negative. You could draw another resonance structure for this or draw it for this one, either way. In any case, that's ozone. Now you may also recognize ozone because it's that kind of funny smell that you sometimes get after a thunderstorm, especially if there was lightning. The lightning in the air causes a little bit of ozone to form, and it has a special smell to it. Ozone forms naturally in the atmosphere to a small extent. It goes up into the upper atmosphere. We call it the ozone layer. It protects us from some of the sun's ultraviolet radiation. When you take an alkene and you react it with ozone, the first thing that happens is it forms this weird-looking 5-membered ring with 3 oxygens in it. It's called an ozonide. It's a highly unstable molecule. In fact, so unstable that in some cases it may actually explode. So typically, you're not going to mess around. You're just going to form this, and then immediately you're going to add the dimethyl sulfide in. But you have to wait until this forms to add the dimethyl sulfide in, first, then you quickly add in the dimethyl sulfide. So this kind of molecule is called an ozonide. And what's interesting about it is that in forming an ozonide, ozone literally breaks the molecule apart. So both of these bonds of the double bond disappear. You may wonder, well, how does that happen? What's the mechanism? Well, it goes through this kind of an intermediate in which that bond isn't initially broken, but the 3 oxygens from the ozone directly add on to the double bond, and you get this kind of a thing. And then it does a weird rearrangement where one of these oxygens switches to the other side, and this bond breaks. And the mechanism is a little complicated, so we're not going to worry about the mechanism. It is very interesting, and it's not real difficult. I learned it in graduate school, but we're not going to worry about the mechanism. Just be able to draw an ozonide if you're asked to do so. Notice that it has an oxygen-oxygen bond, which is unstable in itself. It's called a peroxide bond. Plus it has a carbon with 2 oxygens on it, which is in itself unstable, and another carbon with 2 oxygens on it, and that's also adds to the instability. So that's a pretty bad molecule. So next we're going to add dimethyl sulfide. Dimethyl sulfide, as I said, is a sulfur with 2 methyl groups. It's similar to an ether in that it's a sulfur with carbons on both sides instead of an oxygen with carbons on both sides. So it's called a bioether. Really smelly stuff, but useful reagent in this reaction because sulfides tend to get oxidized easily. In other words, you can add an oxygen to that sulfur and form this kind of a compound called a sulfoxide. This particular one is dimethyl sulfoxide, or DMSO. Some of you may have heard of that. It's a solvent, and it's also used to treat pain in the joints of horses. So it's a horse liniment. I'll tell you, some people use it as well for their sore joints. It's not recommended by doctors for that purpose, but my father-in-law, rest his soul, did use it for his joints, and he swore by it. So I don't know. Anyway, that's dimethyl sulfoxide. It's formed from dimethyl sulfide. So here's what happens. You take your ozonide and you add dimethyl sulfide, and you get 2 of the 3 oxygens adding on to double bonds of the carbon, and the 3rd oxygen adds onto the sulfur, so you get dimethyl sulfoxide. Again, it's a pretty complicated mechanism. It's a 2-step mechanism, and if you're interested, you can look at page 234, but we're not going to worry about it. So all you really need to know is that adding ozone forms the ozonide, and then adding dimethyl sulfide forms the ketones and or aldehydes. Here are some examples. It's pretty simple. Any alkene, when you add ozone followed by dimethyl sulfide, you're going to split the molecule right there. You're going to form 2 new molecules. This side, CH3CH double bond O, CH3CH double bond O. This side, CH3CH2CH2C with a methyl, and then double bond O, CH3CH2CH2C with a methyl, and then double bond O. So this is an aldehyde because it has a hydrogen on that carbon. This is a ketone because it has both carbons on that carbon. So in this particular case, we formed an aldehyde and a ketone, and it's real easy. Just take that double bond, imagine stretching it, sticking O's in on both sides, and you got it. Here's another example. This is a stick figure, but same idea. We're going to split the molecule right there. That carbon is going to get a double bond O because it had a double bond C. That carbon is going to get a double bond O because it had a double bond C. And so in this case, we end up with 2 aldehydes. Now that's an aldehyde because that carbon has a hydrogen, although it's not shown in this picture. There's a hydrogen here. It's not shown in this picture because it's a stick figure, but there is a hydrogen on there. And so that's an aldehyde. This also has a hydrogen on it, so it's another aldehyde. So 2 different aldehydes in this case. This is a little bit different case in that this is an asymmetrical alkene. If we break it right there, you'd end up with a molecule of this from this half, and from the other half, you'd end up with another molecule of this. And so in this particular case, because it's a symmetrical alkene, you get 2 equivalents of the same thing. Notice that I've written the reagent in several different formats here. I've used Me for methyl in this case instead of CH3 for methyl. And in this case, I put both reagents on the same arrow with a 1 and a 2. In this case, I put 2 separate arrows with 2 separate reagents, but it means the same thing. Okay, one other thing to note here is that although this is a trans double bond and it gives these 2 products, if that happened to be a cis double bond instead, it would still give the same 2 products. So cis and trans doesn't give you different products in ozonolysis. This one's a cis, but if it had been trans, it still would have given you the same molecules. Here's some more examples. In this case, we have a ring with a double bond, but the double bond is not a member of the ring as it is in this case. In this case, it's hanging off of the ring. So if we split the molecule right there, this part becomes a cyclohexane with a C double bond O. So cyclohexanone is what that's called. And then this part, which is a CH2, ends up getting a double bond O. So it's CH2 double bond O. That's an aldehyde. Special one has split it here, this is different now. Because the double bond is in the ring, if we split it there, it splits that carbon away from that carbon, but they're still attached by this chain of carbons here. So this carbon becomes a double bond O, and this carbon becomes a double bond O. This one has a hydrogen on it, so it still has a hydrogen here. This one has a methyl on it, so it still has a methyl here. I've drawn it kind of stretched out just because it's hard to draw two oxygens right on top of each other like that. And I actually had to skew them off a little bit, but you can see that it's basically this split apart with a double bond O on that carbon and a double bond O on that carbon. Now also I drew this one in a more typical way of drawing things, which is in a zigzag fashion. So let's just check. Notice that this has a methyl group right there. That's that methyl group right there. And then a C double bond O. There's the C double bond O. And then a CH2, 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 CH2. So there's the CH2, 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 CH2. And then the aldehyde group to CH double bond O. There's the CH double bond O. This is a more typical way of drawing it. If you drew it this way, that would be fine. But you should recognize that this is in fact the same as this right here. Now this is yet a different kind of example in that this is a diene. We have two double bonds in this case. And so we're going to split there and also there. So we'll end up with this part as a ketone or aldehyde. We'll end up with this part as a ketone or aldehyde. And then we'll end up with the middle part with two, a ketone or aldehyde on that carbon and a ketone or aldehyde on that carbon. So this piece will split apart into this. This piece right here, two carbons, will split into this, two carbons. In the middle we'll have a C double bond O, and a C with a methyl group, and a C with a methyl group, and then another C double bond O. So C double bond O, C with a methyl group, C with a methyl group, another C double bond O. So if there are two alkenes, you're going to split it into three molecules. Okay, so here's some for you to do. Go ahead and write down these starting materials and try to figure out what the product is going to be in each case. I'll stop the video and draw them out, and then we'll be back in just a minute and I'll show you what the answers are. Okay, I'm going to go to the next slide now. Here are your answers. So if we split this right here, we'd have a C double bond O and then a CH2 CH3. There's a C double bond O and then CH2 CH3. We'd have the cyclohexane group. It doesn't have any double bonds to it, so it's still intact. And then another carbon that is going to pick up the double bond O. So there's the other carbon, it's going to pick up the double bond O. Now this one, notice, is symmetrical. So if we split it right here, we're going to get two molecules of the same thing. This, I think you can see, is the product from this part. Two methyl groups on a CH, and then a C with a double bond O, and then a CH3. So that's that right there. This is the same product that you would get from this side, just rotated 180 degrees. This one is a double bond in a ring, like that other example we saw. So we're going to split it right there. That's going to become a double bond O, and that's going to become a double bond O. So there we go. Here's that ethyl group, and then a C double bond O, and then a CH2, and then a carbon with a methyl, and then another carbon with a methyl, and then a CH2, and then a CH2, and then a CH with a double bond O. That's that CH with a double bond O. Again, I drew stretched out, and you can see that if we start right here, that's the C double bond O, that's that one, and then a CH2, CH2, so that's that CH2, CH2, and then a C with a methyl, and another C with a methyl, so a C with a methyl, and then another C with a methyl, and then a CH2, double bond O, CH2, double bond O, and then the last ethyl group, So these two things are the same as each other. So here's a question. If ozonolysis breaks molecules down into smaller pieces, what good is it? You know that chemists don't want to break molecules down. Typically they want to build molecules up so that you build bigger and bigger molecules. But this isn't doing that. This is breaking it down. So what good is it? Well, imagine this. We have an alkene. That would be right here. We don't know what it is. It's a bottle. We know it's an alkene. Got a bunch of liquid in it, but we don't know what the structure is. If we use ozone and we break it down, we get two smaller pieces that we can separate out from each other, and maybe we have a chance of figuring out what is that piece and what is that piece, and if we can, then we can figure out what the original alkene was that it came from by working backwards. So for example, let's say that you have a bottle, and in the bottle is an alkene. We don't know what the alkene is, so we take out a little bit of it, and we react it with ozone, and we get these two molecules from it. That's these two. So how do we figure out what the original alkene was? We're going to take these two molecules and we're going to turn them in such a way that the double bond O's point at each other. So notice this is the same as this. this right here, just turned sideways so the oxygen is pointing to the left. This one is the same as this one, just turned so the oxygen is pointing to the right, and then they're pointing at each other. And then what we're going to do is just erase those two oxygens in the middle, extend the bond across between those positions, and so the original alkene must have been that. So that's 3,4-dimethyl 2-pentene. So 1, 2, 3, 4, 5 carbons, double bond between carbons 2 and 3, so it's 2-pentene, and then 2 methyl groups at carbons 3 and 4, so 3,4-dimethyl 2-pentene. That might be a quiz question. If I gave you these two products, could you tell me what the original alkene was? One thing to notice is I drew this alkene with a Z configuration on the double bond. It could just as easily have had this methyl group pointing up, in which case it would be the E configuration. We can't tell from doing this kind of experiment, so that's one thing that this doesn't tell us is whether the original alkene was cis or trans. Okay, here's another thing. We can, in some cases, form interesting molecules with two functional groups, in this case an aldehyde and a ketone group, from an original alkene that was in a member of a ring. And so basically, if you start with an alkene with one functional group, you can break it into a single molecule with two functional groups. So you're literally expanding your molecule from one to two functional groups. That's a useful thing to do. So can you tell me what was the original alkene that this keto-aldehyde came from? So again, stop the video, redraw this in such a way the oxygens are pointing at each other, extend that carbon-carbon double bond between those two carbons, between that one, and that would give you your original alkene. So stop the video, try drawing that out, and I'll show you the answer here in just a minute. Okay, we're going to move to the next slide. So what I've done is I took this molecule and I redrew it in such a way that this oxygen double bond is pointing at this oxygen double bond. So there's that one, and there's that one. Let's just make sure this is right. So we have a carbon with a double bond O, carbon with a double bond O, then a carbon with a methyl group, so carbon with a methyl group, then a CH2, so it's a CH2, then a carbon with a methyl group, that's that one, then a carbon with a double bond O, that's that one, and then another methyl group right there. So this molecule is the same as this molecule. And then I'm just going to put my finger over those two oxygens or erase them or somehow extend that double bond between those two carbons. That becomes that one. And so this must be the original alkene that this came from. And there it is. This would be 1, 3, 5 trimethyl cyclopentene. So it's carbon number 1, number 2, number 3, 4, and 5. 1, 3, 5 trimethyl cyclopentene. And if you break it right there, you would in fact get that molecule. So the quiz question would be, if you wanted to make this